Welcome to Scale Up University. Welcome to the course on designing data intensive applications. So, this is the lecture 4 of module 1. And in this lecture, we will discuss understanding reliability in data systems. So, if we look at the lecture overview, like what exactly we will be discussing in this lecture, understanding reliability in data systems. So, the idea is see, if we talk about the end users, they don't care how your system works. Like they are not at all concerned about the internal working of the systems. They only care that the system should work and it should work every time. So it's like a very important point I am discussing with you, because the end user of the tech product you are making or the computing system, so end user is not at all concerned about its working, internal working. They only care that it should work and every time it should work. And that is reliability. Reliability means users can rely on systems, like they know that it will work no matter what. So that is reliability. So most systems, they appear reliable when traffic is low, when nothing fails, and when everything is normal. So under normal conditions, when the traffic is low, when everything is working perfectly fine, so we call it the normal state. So in the normal state, definitely the system may appear reliable, but the real systems, it operates under very rigorous conditions. So real systems, they operate under failures, they operate under overload, they operate under human mistakes, where human can make mistakes while operating the system. And real systems, they operate under partial outages. So from here, we can say that reliability is not about normal operation. Like when the system is working perfectly in the normal state, then we can't claim the system to be reliable. Reliability is not about normal operation. Reliability, it is about behavior under stress. So in order to test whether the system is reliable or not, we have to check its behavior under stress. Under stress, how the system is behaving, like the under failure, under overload, under human mistakes, under partial outages, how the computing system works, that will decide the reliability. So that's the idea. So that is what we will be discussing in this lecture. So this lecture, we will be talking about reliability in data systems. We'll understand reliability in data systems. So if we look at the topics that we will be covering in this lecture, so we'll look into the definition of reliability, reliability versus correctness versus availability. So all these are different. Reliability is different from correctness. Correctness is different from availability. So we will look at the differences. What does it mean for a system to work correctly? Faults are inevitable. Reliability is about handling them. Trustworthiness of data systems. And finally, we will conclude this lecture by discussing reliability is a spectrum, not a binary. So all these topics we will cover in this lecture itself one by one. So this is the module 1, trade-offs in data systems architecture, lecture 4, understanding reliability in data systems. And we will be starting with the first topic of this lecture, that is definition of reliability. So if we talk about the formal definition of reliability, a system is reliable if it continues to function correctly even when things go wrong. So if the system can work correctly, if the system can function correctly even under stress or even when things go wrong, then we call the system to be reliable. So a system is reliable if it continues to function correctly even when things go wrong. So reliability assumes faults will happen. Reliability assumes components will fail, and reliability assumes users will behave unpredictably. So whenever we are designing systems, we have to keep this in mind. Like as data system designers or system designers, we have to, because in the previous lectures also we have seen that faults are something which are inevitable. Faults will happen, components will fail, and users will behave unpredictably. And as system designers, our goal is to handle those scenarios so that system functions correctly despite of fault in the system. Despite of components failing in the system should keep on working, keep on functioning correctly. And despite users behave unpredictably, systems it should function correctly. So that is reliability. So whenever we are trying to like design a reliable system, so reliability means system should function correctly despite things go wrong, like despite faults will happen, despite components will fail, despite users will behave unpredictably. Now, one very important clarification we have to discuss, like a very important clarification. So if we talk about reliability, it does not mean no failures ever occur. Okay, so it's very important. So so reliability does not mean no failures ever occur. It means what truly it means is failures are handled gracefully. So reliability means handling failures gracefully, the system recovers. Reliability means the system should recover under stress, under conditions of failure. Data integrity is preserved. So the system should preserve the data integrity. So all this is like very important. So now we are getting a feel of reliability. So now it's very clear to you that when I tell that a system is reliable, it means the system will continue to function correctly even when things go wrong. System is capable of handling failures gracefully, recovering after failures, and preserving the data integrity. So here one very important learning, we should not expect perfect environment. We should not even assume perfect environment. And if we talk about reliability in data systems, so this is very important because in this course we are talking about data systems, data intensive applications. So in data systems, reliability means no data loss unless explicitly allowed. So in a reliable data system, there should not be any data loss, no silent corruption in the data, no inconsistent states, and predictable behavior under failure. So all these things leads to reliability in data systems. Reliability versus correctness versus availability. Now see, all these are different terms like with different meanings. So if I talk about correctness, so correctness means, if I talk about correctness, it means the system produces the right results according to its specification. So correctness means whatever the system is supposed to produce, it is producing that. So the system is producing the right result according to its specification. That is correctness, and it makes sense also. If we look at an example of correctness, like if we look at some examples, bank balance reflects actual transactions. So in banking systems, correctness is very important wherever where bank balance it matches with the transactions. Like whatever credit and debit we are doing, bank balance should match that. And order is charged exactly once. And in an e-commerce platform, order should be charged exactly once. So that is the correctness. A user sees their own data, not someone else. Yeah, user should look into their profile and not someone else. So that is correctness. So one very important point, correctness is about logical validity. Now let us discuss availability. Availability means the system responds to request. Okay, this is very important. So availability means the system should be available wherein always it should respond to the request. So if the system responds to the request, we say that the system is available. And if the system is not responding to the request, then we say that the system is not unavailable, not available. So here one very important point, even if the response is slow, that's okay. If the data is slightly stale, like if the data is slightly old, that's fine. Some functionality is degraded, then also it's fine. So but the core principle is that the system must respond. So the system should respond to the request. Even if the response is slow, it's fine. Even the data is slightly stale, it's fine. Even if some of the functionality of the system is degraded, that's also fine. So availability is about system responding to incoming request. So availability is about uptime and responsiveness. Okay, now we'll talk about reliability. So until now we saw correctness. So correctness is about logical validity, wherein the system produces the right results according to the specification. Availability is about uptime and responsiveness, wherein the system responds to incoming request. Now we'll discuss availability. Now reliability. Now we'll discuss reliability. So reliability, it is like bit broader. So reliability, it includes correctness. Reliability includes availability. This is very important. And reliability also includes recoverability, because we already saw reliability means how the function handle the failures gracefully, how the function recover from the failure. So reliability also include recoverability, and reliability includes resilience to faults. So this is like very important. So reliability means correctness, availability, recoverability, and resilience. So that's the reliability. Now let us look at one very important insight. Now see, a system can be available but incorrect. So this is very important because we saw that in availability, stale data works or inconsistent data works. So availability is about responding to the request. Now availability does not guarantee correctness, because the system might respond some inconsistent data. So the system might return stale or inconsistent data. So since the system is responding to incoming request, we are calling it to be available. But since it is returning stale or inconsistent data, here correctness is compromised. The system is not correct. So this is very important. So we saw that a system can be available but incorrect. Similarly, a system can be correct but unavailable. So the system is safe, but it is down, like it is not responding to incoming request. And also, if I talk about system, it is available and correct. System can be both available and also correct, but unreliable under stress. So what it means is that under normal state, under normal state, system is both available, it is responding to all the incoming requests, and it is giving the correct output, like logically valid. But under stress, it might not handle failures gracefully. It might not be resilient to faults. So hence, under stress, it might be unreliable. So this is like a very important point we discussed. So from here, we can say that if I talk about reliability, reliability means, can I trust this system over time? And it includes behavior during crashes, behavior during overload, behavior during partial network failure. So how the system behaves under stress or under abnormal conditions, that will help us in determining whether the system is reliable or not. So let us look at a table to get more clear insight. So if I talk about the correctness, so correctness is about giving right answer, and example failure is wrong balance calculation. If I talk about availability, it is about responding on time, like responding to the incoming request. So availability means if the system responds, and example failure means server returning 500 error. It means the system is down. And reliability means survives faults gracefully. And example failure is data corruption after crash. So let us suppose any crash occurred and data got corrupted, and hence the system is not reliable because system was not able to handle the crash gracefully. So that's the idea. What does it mean for a system to work correctly? So if I talk about correctness, so correct according to what? So when I tell that system is working correctly, so correct according to what? So correct according to business rules, correct according to invariants, correct according to data constraints, and correct according to user expectations. So the idea is that system should work according to the business rules, invariants, data constraints, and user expectations. Let us look into an example of bank transfer. So let us suppose Alice transfers rupees 1000 to Bob. Now, ideally, what should happen is that when Alice will transfer 1000 rupees to Bob, Alice bank balance should decrease by 1000. Bob's bank balance should increase by 1000. Total money in the system should be invariant because no, whatever got debited, same amount got credited. So in the system, like when I consider both the accounts, the total money should be same, invariant, and transaction should occur only once, exactly once rather, and order of operations are preserved. So all these are like important things to consider, and if any of it gets failed, if any fail, then what will happen is money disappears, money duplicates, balances mismatches, the system is incorrect. Let us look at one more example to understand what does it mean for a system to work correctly. Social media feed. So here correctness may mean you see your own post, you don't see deleted content, likes count is roughly accurate. So here in social media, the idea is that I should be able to see my post, I should not be able to see the deleted content, and like count should be roughly accurate, eventual consistency. And here one very important observation we can see here, in social media, the correctness is looser than banking, because here we are okay to have roughly accurate like count, but in bank transfer correctness is very strict. There is no scope for error, but in social media feed, some data inconsistency or some stale data is bearable. So from this we can say that correctness is contextual. In some context we need like very strict correctness, and in some other context we are okay with some nominal correctness. So different systems require different guarantees. Strong consistency, idempotency, eventual consistency. So the idea is that some systems might require strong consistency, some systems are okay with eventual consistency, some systems they need idempotency, some systems they want exactly once processing, and some systems they want ordering guarantees. So this is the idea. Faults are inevitable. Reliability is about handling them. So see, we have been discussing this point in this course. Like real systems are not perfect, faults are inevitable. Real systems do experience faults and hence failures. So if I talk about real systems, it experience disk crashes, it experiences memory corruption, network partitions, software bugs, operator mistakes, traffic spikes. So for real systems, faults are inevitable. It do come across many abnormal, uncertain situations wherein it drift away from its normal state. Real systems experience disk crashes, memory corruption, network partitions, software bugs, operator mistakes, traffic spikes. Now, reliability means handling those faults and failures gracefully, handling the abnormal situations gracefully. So, reliability means under abnormal conditions, data is not corrupted. It is very important because in data systems, we cannot afford the data to get corrupted. So, data is not corrupted. System recovers. So, reliability means system recovers gracefully. Invariants remain intact. Failures are visible, not silent. So, this is also very important. Failures should be visible and it should be handled gracefully because silent failures are the worst failures. Because silent failure means we will not be able to handle it, and visible failures means we know that okay, a failure occurred and we can at least try to handle it or try to recover from it. And why silent failure is the worst failure? Because if data is corrupted silently, it is very dangerous. Inconsistencies goes undetected. Duplicate events accumulate. So all these scenarios like failure leads to worse failures. And here what will happen is ultimately the system becomes untrustworthy. Trust once lost is hard to regain. Trustworthiness of data systems. Okay, now this is very important. Trustworthiness of data systems is very important. Like reliability is the key to trust because reliability it ultimately leads to one thing and that is a trust. So we can achieve trustworthiness of data systems via reliability. So if I talk about what makes a data system trustworthy, and the answer is reliability. And when I talk about reliability, I'm talking about predictability. Means behavior is consistent under similar conditions. That is the predictability. Transparency. Failures are observable. So if the system is predictable, transparent, recoverability, if the system can restore valid states, that is recoverability. And integrity. Data is not silently corrupted. That is integrity. So in a system, like data system is trustworthy if it is predictable, transparent, recoverable, and integrity is there. Then we can trust the system. Now, why trust is central? Trust is like very important. See, users now they will forgive slow responses, and it's a very important observation. It's a fact that users they will forgive slow responses. They will even forgive minor outages. But unfortunately, users they will not forgive lost money, lost data, privacy breaches, incorrect records. So lost money, lost data, privacy breaches, incorrect records, users will never forgive. So we should treat data systems as institutions. So if we talk about banks, hospitals, governments, and AI systems, they all rely on data. They all rely on trusted data because when data cannot be trusted, business collapses, legal consequences follow, and reputational damage occurs. So for any institution, data system plays a very important role. Trusted data is the key because when the data cannot be trusted, then business collapses, legal consequences follow, and reputational damage occurs. Reliability is a spectrum, not a binary. Okay, this is very interesting. So see, reliability is not like, okay, system is reliable, system is not reliable. We cannot say like that. It is not a binary thing, yes or no. Like system is reliable, yes or no. It's not like that. Rather, it's a spectrum. Means we can say that the system is 80% reliable, 90% reliable. So it's a spectrum. And one more very interesting observation, no system is 100% reliable. No system is 100% reliable. And reliability, if we talk about, it depends on acceptable failure rate. It depends on expected operating conditions and business risk tolerance. So reliability is a spectrum. So whenever we are deciding the spectrum or designing the spectrum, we have to answer some questions like, what are the expected operating conditions? What is the acceptable failure rate? And what is the business risk tolerance? So here we can see the reliability spectrum. So from 0 to 100%, and as we are moving towards 100%, reliability is increasing. And along with that, because of increasing reliability, cost and effort is also increasing. Now, 100% reliability is like it's theoretical ideal. Now, 99.9%, let us suppose a reliability, or 95%, and 0% means unreliable. Like we have a scale. So any system like if we are measuring the reliability, it's not a binary thing, rather it's a spectrum. Let us look at one example of like a blog. Now we say that the uptime may be 99% uptime may be fine. So here the measure of reliability is 99% uptime. And for payment processor, so for blog 99% uptime is fine, but for payment processor 99% uptime is catastrophic. Why it is catastrophic? Because that 1% downtime, it will lead to very big losses, because all those payments will not get processed. So 99% uptime is catastrophic for payment processors. So idea is that in reliability, if we talk about, context matters a very big role. Different applications have different needs and different reliability needs as well. So that's the idea. So finally, we completed this lecture. So in this lecture, we saw the meaning of reliability. We saw that reliability means functioning correctly under faults. It means correctness, availability, and reliability. So in this lecture, like we saw that correctness, availability, and reliability are related, but they have different meaning. Correctness depends on system invariance. Trustworthiness is the ultimate goal of any data system. Reliability is about behavior under stress, not normal operation. I hope you got a very good understanding of the concepts which we discussed in this lecture. So do subscribe to our YouTube channel, Scale Up University, for more such interesting concepts and lectures. Thanks for watching. Thanks for your time.